Okay, so we're going to begin chapter 7. So I think this picks up on a place in the curriculum that we were kind of working with a lot last year. We were working with integration a huge amount, right? But where we left off, and then we got into some differential equations, which is kind of a throwback to more derivatives. So we're going to work with a lot of integration in this unit and start to see some of its applications. This is kind of the applications of integration unit. I don't know if I really think about it as like so much problem solving though. There's a lot of like things you can do with integration in here though. Like how much work does a fluid do when it's pushed through a certain elevation? We'll have things like that. And then basically also just simple things like how do you find the area between one curve and another? So I kind of tried to draw two random curves here. And there's this one element in this chapter which is going to be quite prolific, very common. And that is the focus on an infinitesimal rectangle. Can you guys see my infinitesimal rectangle in this generic problem? Someone describe it? It's the
difference in change in...
What color is it? I'm looking for it.
Yes,
It's the red one. So I realized that it's impossible, and you guys should realize too, that like when Isaac Newton was thinking about these things way back in the day, and he was sort of thinking about infinitesimals, you guys should have heard that word before, right? Infinitesimally small is like infinitesimally small. Can you really draw something infinitesimally small? No, so this is just like a thought diagram of that. So here's the infinitesimal rectangle. So to find the area shaded in this light blue color, we're just going to add up all those infinitesimal rectangles. So all we've got to do is figure out like what's the dimension of each rectangle, and we're good to go, right? So as a sum, in other words, as an approximation, this area is equal to the sum. I'm not even going to put indices on the sum because we'll just leave it in general. Of what? What is that rectangle's area? Can you guys tell me? What's its width?
0.
Infinitesimally small, right? But what did I call it? Very good, but I called it dx because that's the way you represent infinitesimally small quantities with calculus notation, right? So the area of a rectangle is the width times the length, or the height in this case, right? So how high is this rectangle?
Change in height.
The change in what? You got some labels here, we'll use them. What's the top? Wouldn't you go F minus G? Top minus bottom is the idea here. There's two approaches to these rectangle problems. There's top minus bottom, and there's right minus left. So we're going to be using both. And in fact, usually if it's not actually infinitesimally small, if it's actually a rectangle like that, instead of writing dx, what should I really have said? Shouldn't I have gone for our little Greek delta x? I think so. So in a sum, it's delta x for the width. My Calc 1 students will need to stop giggling, I'm sorry, but thank you. So we've got that, and then we've got this part is going to be for us f of x sub I minus g of x sub I. So that's height times width equals the area of said red rectangle. Add up all red rectangles from here to here. That's how we'd have to mess with the indices here, right? And you get the area between the two curves. So take that and turn it into calculus by saying, if we take, what kind of thing do you need to do? What do you need to put in front of this to make it exact? You need to make these rectangles go smaller and smaller and smaller, and take a limit as what, Derek? Can you help me?
Limit as change in x approaches 0.
Yeah, there you go. Perfect. When you actually do that limit of the sum, I think we've done this before. This is an argument that we've used more than one time already. You get the integral. That is where we started explaining what integrals meant with area. So this is the integral from, let's call this starting spot A to that ending spot B of generically top minus bottom dx. That's how you find the area between two curves. I think we kind of already did a couple problems like this, but there's a little more theory. Any questions so far? Sweet. Let's do a couple examples. All right, so our first example, finding the area between curves using top minus bottom approach. So first I'm going to try to sketch the region that I'm trying to use here. Sketching in this unit you'll find is pretty important, so try to do your best artwork. I really sucked at that in high school, but do your best. You'll be rewarded. So x squared plus 2 is of course a parabola shifted up 2. Something like that, right? Negative x is your line with intercept 0, down 1 over 1. There's that. That's the vertical line, right? Vertical or horizontal? Vertical. Of course it's vertical. So I'm going from here to like here. So the region between all those is this guy, right? So what I'd recommend you doing on almost all problems in this unit, when you've got some kind of visual involved, is sketch your infinitesimal rectangle and work from it. It really gives you a spatial to look at and think about rather than just a theory. So I'm going to sketch my infinitesimal rectangle in there in red, and I'm going to think about integrating that rectangle from where? From where to where? You guys should know. 0 to 1, there you go. So this area is going to be the integral from 0 to 1, there to there, rectangle, 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 rectangle. What are the dimensions? That helps to label these, right? So I'm going to go top minus bottom. Simplify. And that's a pretty easy integral to do. Let's wake up our summer minds. What's the integral of x squared? What's its antiderivative? Forget about the 0 and the 1.
Oh, it's 1/3 x to the cube.
Good. Somebody else besides Derek, what's the integral of x?
1/2.
And the integral of 2? Sweet. We're live, and we should go like this, right? Something like this.
Do we need our C?
No, because this is not an indefinite integral question. It's a good wake-up question, isn't it? Okay, so let's plug in. So we're going to get what? 1/3 plus 1/2 plus 2 minus 0, 0, 0, minus nothing. So that's what? Common denominator 2/6, 3/6 is 5/6 plus 2, that's 5/6 plus 12/6 is 17/6. There are 17/6 square units of area in that little blue thing. Sound right? So even if the problem doesn't have that, just to get yourself thinking dimensionally, we're going to be doing volume, we're going to be doing area, I would just stick a units squared here, especially if you're in physics at the same time, because you always never want to leave those units off. You'll get marked off big time. It sucks. I know. So I'd just go for that, because this is area, right? Let's do one more. You guys have your calculator? I think we're going to use our calculator to help us on this one. If you don't, get a friend.
On mine.
So let's do another top minus bottom problem. Two curves, say F and H. This one we should be able to graph without a calculator, honestly, because you could factor it and find its zeros and stuff. This one, maybe, actually, you can factor this plot an X.
Wait, why is there 2x?
Well, let's just use our calculator, okay? So use your calculator to get a nice picture of the base region. I think this has a little bit of a difference from the last problem.
I noticed that a lot slower at night.
There's the parabola. We knew we'd get a parabola and a snake, right? So the region between the curves, what's different about this problem? Somebody tell me?
You have two regions?
There's more regions. How many? Is Katie right? 2?
Probably 1, 2.
There's this one, right? So you want to sketch this on your papers. That's what I'd recommend in your notes. Just do a quick sketch. There's that part and then this part, right? They're not symmetric. If they were symmetric, you could just double one and shortcut the problem, right? I'd recommend looking for symmetry. It'll help you do faster things sometimes. I think we're going to have to do this as 2 separate integrals. So we're first going to go the integral from, how do we figure out where this is? Intersect, right? So find that intersection. Somebody find it for me. I've got my notes. You guys should all be able to find it. Find it. Remember, it needs to be exact, so don't actually calculate it. Is it -2?
-2.
All right. So where's the next time that the 2 curves intersect? It looks like where? Looks like 0. Confirm it. A couple of us should confirm it at least. It's actually 0. It is. Okay, so what are we integrating though for this first piece? Which curves on top, which curves on bottom? This is the parabola, right? So the cubed one is on top first. Top minus bottom. I'm going to just distribute this in advance. You guys cool with that? Make sure you watch out on your distributing though. So I'm going to do it in advance. So minus a negative is plus. And it's that plus the other area from 0 to, where do they intersect again? It looks like 2-ish. Is it 2? Is that a 2? Guess I could confirm it with you guys. It is. So 3x cubed minus blah blah blah.
No.
It switched on this time. This problem, it happened coincidentally. Each problem's different. It's a switch. Now the parabola is on top. Minus this. Minus, plus, plus. Before you actually do those 2 integrals, what should you do? Like terms, right? Put your like terms together and then integrate it. I'll give you guys a few minutes to see what you get there. The right answer is 24. And if you think about how big these areas are, I think that seems ballparkish to me. Is the area in each quadrant, how big is the area in each standard quadrant? If it's 10 to 10, 100. So this looks like it could be 24 to me. So make sure you get 24. If you're watching the video, I will put the calculations up in just a second. But I'd pause it and try them yourself.
I got like negative 12 showing thirds.
Oh, I have a mistake too. Credit. Lots of the same kind of numbers. Let's see.
Yeah, I didn't think.
How'd you get that 12 on the bottom?
Where?
Under 3x, 4. How'd you get that 12? Shouldn't that be a 4?
Yes. Thanks, man. Let's see if that's it. Lots of yucky numbers on this one, man. Let's see. So 0 minus negative 2, that's going to be 16 over 4 is 4, that's 12. And then negative 2 here is going to be minus 24 plus. Let's go 2 in, so that's 16 over 4 is 4. Negative 12 plus 4 minus is going to be negative 12 minus 24 is negative 12. Boom. One tiny little mistake did it, yeah? Thank you, Gabe, for catching that. It was nice. It was pretty fast. So I just had a 12 here. It's supposed to be just over 4, right? Okay, did I make that calculation clear enough? Anybody confused about part of it? You can see that I was really trying to be careful. You see me erase my work a couple times on this one since we've got 2 integrals. And I'm really trying to be careful with this because you can easily misplace a minus, you know what I mean? If you got to stick 0 in, which comes out to 0, then you got to stick this in. And remember, the fundamental theorem of calculus part 1 said that when you stick these in, what goes in the middle? Minus or plus? F of b minus f of a, right? So you got to make sure you get that minus. That's sneaky sometimes in problems like this. Same thing, it's right there. So the negatives can easily get you on that if you aren't careful about writing it out and you're trying to be too clever. So that's about the minimum amount of work I'd feel comfortable with if I was like turning this into my boss or my teacher. You do what you gotta do though. All right, tomorrow we will look at integrals of the same sort, but this time what if we have a horizontal infinitesimal rectangle? Because that's sometimes more convenient. All right, so let's look at another problem, finding the area between 2 curves. So in this case, we're going to do so without our calculator. That's definitely half of the AP exam. So you got to be able to function without your calculator for simpler functions. So this is one with a parabola and a line. We should be able to draw that without too much trouble, right? So let's see, a parabola that has been shifted up 2 in this case, right? So I'm going to have a parabola up by 2. And flipped over this way, something like that. You got a straight up line, y equals x. The transformate that's the inverse line, right? 45 degrees, something like that. So the region that's formed here is pretty obvious. It's just this half circle looking thing up there, right? So our first task is to figure out where we're integrating from. Well, we're integrating from this intersection to that one. We have to do this in 1 or 2 integrals, you guys? 1. Just 1, right? If we're doing top minus bottom, we're going to do a left minus right one here in a second. So let's put in our, what did I call it yesterday? Anybody remember what I called it yesterday, this thing? Infinitesimal rectangle. Very nice. So there's our infinitesimal rectangle. You guys are like, why do I need to draw that, Mr. McGee? Like, it's crazy. I'm telling you, draw that throughout this chapter and it will make your life easier when we get to harder problems that are a little less intuitive than this one. Okay. So there we go. Top minus bottom is the way we're going. We've got to find these intersection points. That means we need to see where this y value is equal to that one. So in other words, I need to solve the system that says, if you substitute it, that. Does that make sense? Where the 2 y values are equal. So I'm really doing a system of equations, 1, 2 equations, and I'm solving for where those intersections happen. So that's a parabolic thing, right? It's a nonlinear system of equations. So I'm going to set this to 0. So like that, multiply through by -1. And does it factor? Could use the quadratic formula if it didn't, but it does. So now I'd eyeball this and see if that makes sense. Do you think this value could be -1 for x, and that value could be
That's +2 and -1, isn't it?
like that, right? So my drawing looks a little bit off, honestly. Let me double check. You guys get something different?
It's +2, x +2, and then times.
Oh, I'm not doing my factoring correct. Oh my goodness. I think this is going to happen a lot this year. You guys are going to have to keep me honest, because I'm like running around like crazy in the morning. I can't wait till we get to the afternoons. I was like, that doesn't look right. You guys see how we knew something was wrong? And I was like, something's wrong here. It's because it didn't look right according to the picture. That was not right. So it's this. That looks right. -2 is over here to 1. Okay, so our integral is -2 to 1. And we're going top minus bottom. What's on top? What's on bottom? No like terms, just got to do it. So 2x minus x cubed over 3 minus x squared over 2, all from evaluated at -2 and 1. So that's going to be, if we put 1 in first, 2 minus a third minus a half, and then we're going to have, plugging in -2, -4. It's going to be negative because it's odd, so what is that, +8 over 3? You guys agree with me? And then plugging in -2 is going to stay negative and be 4 over 2 is 2. You're right. Thank you. And now we just got to simplify this mess and try to make it look nicer. So let's see, 2 minus -4. You do this little math like you want. I mean, if you're having trouble by now, I don't know why you're in here. None of you have trouble with this kind of stuff. So, but let's see. So we've got, should we make a common denominator of 6ths for everything else? I'm just going to do that. That's my preference. So I'm going to say this is -2/6 minus 3/6 minus 16/6. For that one, careful of that. And then, oh, there's another -2, huh? Another +2, so that's 8. 8 and this stuff. So how many 6ths do we have? -21? You guys follow me? It's a little dangerous. You guys might want to take it a little slower. I don't know. Probably not. That's 48/6 minus 21/6. It's going to be 27/6. That's the answer. I bet it reduces though. Divide by 3 is 9. Divide by 3 is 2. 9 halves, 4 1/2. And that was the answer I got a second ago. Okay? Sweet. All right, let's do one with horizontal rectangles, and then I think you guys should be pretty good on this section. By the way, any of these we could have done with horizontal rectangles. Sometimes horizontal is a better, easier way to handle the problem than vertical. That's the only reason we're going to learn about it. Also, a lot of you during your project, for whatever shape you want to visualize, are going to end up using horizontal stuff. So we definitely want to be comfortable with it. The project will make you strong. Usually people have some issues with the project, like they have to get some help from me or their friends, work through things, and it gets a little tough and dicey at a few points. And then when they're done with their project, they're like, Chapter 7 problems. Please, I'm telling you, that's the way it works. For people who put in the work on the project, every single person is like, yay, an AP problem on Chapter 7. I get 100%. That's the way it goes, I'm telling you. That's one reason I do that project. So let's see. I was thinking this one. So integrating horizontally. So I was thinking we'd find the area bounded by area of the region bounded by this is a problem that if you did it vertically, it's probably possible, but it might be more difficult. So first of all, let's picture this, and I don't think we should need a calculator to picture this one either. These are fairly simple curves, yeah? So, you guys all know what x minus 1 looks like, so let's do that one first. Y-intercept, slope. This is a sneaky transformation one, right? You've got to factor the negative inside first. So negative x minus 3 is the same thing, and easier to read. That means it's a square root shape shifted right by 3 and then flipped horizontally, right? It's negatives inside. So we're going to go right by 3. That's 1, 2, 3. Square root shape, but flipped horizontally. Yeah? And it's plus or minus, right? So minus is that one. Questions? That's the stuff they're going to be working on in like a couple days, right? That kind of stuff. So the region between these two is, again, I think pretty obvious. Is this half circle looking dude. So tell me why, somebody tell me why, if you use the top minus bottom approach and use a vertical infinitesimal rectangle, you might run into issues on this problem. Ms. Slade, do you have an idea?
It's not really top, they're both kind of...
They're both kind of top-ish. I like it, that's good. You can do it still, but it sucks on this one. You have to be a lot more clever than we've been being. The top from this intersection point to that intersection point is the line. So you go line minus that negative root. But then it changes. Then you have to use this positive root as the top and the negative root as the bottom, wherever that intersection is. You'd have to do it in two different pieces, which isn't that bad in and of itself, but there might be more intricate parts to that too. So why don't we just do right minus left, do horizontal rectangles, and just do one? Does that make sense? Because right minus left, is it going to be, think about it, right and left. Is one curve going to change from being the right and the left, or is it just going to be all one shot? It's all one shot. I said that badly, but if we do this as our infinitesimal rectangle, this thing's always on the right, that thing's always on the left. That's easier, okay? And sometimes you really even can't avoid it. You can't do it the other way on some occasions, or it's incredibly difficult, okay? So that's the reason to even consider doing it that way in the first place. What are the dimensions of this infinitesimal rectangle? What's this dimension? dy. And this dimension is, of course, right minus left. If you're confused why it might not be left minus right, just think about how distance works on something really simple. If you're over here and you're like between -7 and -3, do you go -3 minus -7, or do you go -7 minus -3? Think about which way that goes. The distance between -7 and -3 is obviously 4, right? But which way does it go? Let me be a little more precise. I see some eyes. Here's -7. You want to know the distance between here and here, for instance, over in this land. Of course it's 4. But how do you get that it's 4 with math and make it come out the same way every time? You go left minus right, or right minus left. It's right minus left. Try it both ways and you'll figure out, hey, really I go right minus left. That's why for this, in all cases, you always go right minus left. Okay? So let's set up the integral. So we're going to go integral from that spot to that spot. How are we going to find the two intersection points? just like last time, we could solve the system. I'm going to shortcut that this time. You guys want to see me solve the system by hand, or?
Not really.
I think you can handle that. I'm guessing you guys are all good enough at that. So this point, if you solve the system of equations, this one, and do some FOILing and all that good stuff, you're going to get that this point is -2, -2, and this point is 1, 1. Okay? So the key here is that you remember that whereas before we were focused on x's, now we're focused on y's. So everything had better be in terms of y's. So our area is going to be from where to where, y-wise. From -2 until 1. But you're thinking like this. It's coincidence that those are both repeats.
I don't think one is an intersection because unless it's wait.
It doesn't.
No, it would be because if you put
Yeah, because the intercept for the.
It's 2, 1. Haha.
1, 1 doesn't work for the second one.
I looked at the wrong problem. Yeah, it totally doesn't. This is me being late in the day again. Thanks, Katie. This is -1, -2. That just looked terrible, didn't it? So I love that you guys are alive more than me. Jeez. Okay, so -2 up to 1. I had that part right. Thanks, Katie. All right. So now we're going to have to put right minus left. dy. There's a big notational helper here. These functions should be in terms of what? Y. Are they in terms of y yet? No. So how do you fix that? Yeah, you solve them. You take the inverse of each one, right? Because that's the same function. This and this are the exact same function, except this one is in terms of y as the independent variable. This is x of y. You aren't used to doing that, but now you need to. And we can do the same thing with that one, right? By doing a couple steps. So is this guy the right or the left?
That's the right.
The line. Is the line the right or the left? It's the left. So we're going to go minus y minus 1 or plus 1. You've got it, Anna. And then we got to solve that guy, so we're going to go square both sides. Solve for x, right? So there's x of y for the other curve. And now we're going to substitute that in for the right function. And do the integral. And you have your answer. Because this integral is going to be no harder, right? It's just little polynomial stuff like we did before. So, Anna?
The y minus 1 is supposed to be plus.
Yeah, so it's once you distribute and everything, sure. Yeah. So let's clean it up a little bit. Or were you saying something else?
If you look at it, it's y equals x minus 1, so you add 1 over to the other side.
Mistake. Number 3. Nice catch. I don't really want to put this video on YouTube now. It's going to mess with my pride. But that's okay. So combine those like terms. You guys can do that integral, right? I'm not going to finish it. I'll just give you the answer and you check your work. So before you start on your assignment, check your work. This should come out to, supposedly, if you can trust my notes more than me, which you can. Did I get 9/2 again? Let's make sure I'm looking at the right one. I said it came out to 9/2. You could math 9 it and check it that way too, right? Okay, so check that one, see if you get 9/2, see if I'm a liar, and then you guys can finish working on your assignment. See you next time. Those watching the video, we're going to look at solids of revolution, which applies directly to our project.